A massive volcanic system near Naples is moving again. The ground is rising, small earthquakes are shaking the region, and hot gases are escaping from deep below the surface. Scientists call this unrest. Not a guaranteed eruption, but the signs are important enough to watch closely. Tonight, this documentary follows what is happening beneath Campi Flegrei, why this supervolcano matters, and what scientists still cannot predict. Before the story begins, please like this video, subscribe to the channel, and stay with us as we explore the quiet warning signs beneath one of Europe's most closely watched volcanic regions. The landscape of southern Italy unfolds along a broad arc of coastline where land meets the Tyrrhenian Sea. The region is shaped by long geological processes that extend far beyond human memory, involving the slow movement of tectonic plates and the gradual rearrangement of Earth's outer layers. The African plate moves northward, pressing beneath the Eurasian plate, and this interaction creates a zone of compression, melting, and rising heat over many millions of years. This process forms mountains, fractures the crust, and generates volcanic systems that remain active long after their initial formation. The Bay of Naples lies within this dynamic setting, bordered by low hills and open water that reflect changing light across the day. The sea appears calm at the surface, but beneath it lies a continuation of the same geological forces that shape the land. The coastline curves gently, and along its edge, towns and cities have grown over centuries, adapting to the terrain while relying on the fertile soils created by ancient eruptions. These soils are rich in minerals, supporting agriculture that has sustained population since early settlement. To the east of the bay stands Mount Vesuvius, a well-known stratovolcano formed by repeated eruptions that built layers of ash, lava, and rock. Its presence is prominent, rising above the surrounding land with a defined peak. However, the broader region contains more than a single volcano. To the west, the land appears lower and less sharply defined, yet it holds a different kind of volcanic structure that spreads across a wide area rather than rising into a single cone. The wider Mediterranean environment contributes to the stability of the region's surface appearance. Seasonal weather patterns bring mild winters and warm summers, and vegetation covers much of the land, softening the visual signs of geological activity. Olive trees, vineyards, and small fields occupy slopes and plains, masking the underlying volcanic materials. From a distance, the region appears settled and stable, shaped more by human activity than by natural forces. Yet the deeper structure of the Earth beneath this area continues to evolve. Heat rises slowly from below, carried by molten rock and hot fluids that move through fractures in the crust. This movement is not visible at the scale of the broader landscape, but it exerts influence over long periods. The crust responds by bending, cracking, and shifting, sometimes in ways that are too gradual to detect without instruments. The Mediterranean Sea itself plays a role in moderating surface conditions. Water absorbs and redistributes heat, and its presence stabilizes temperature variations across the coastal region. This influence helps maintain a relatively consistent climate, allowing ecosystems to develop and persist. At the same time, the sea covers parts of the volcanic system that extend offshore, concealing features that would otherwise be visible on land. Across this setting, geological time operates on a scale that differs greatly from human experience. Processes that shape mountains and volcanic basins occur over thousands to millions of years. Within this long framework, periods of activity may appear sudden when measured against shorter timescales, but they are part of continuous adjustments within the Earth's structure. Observations indicate that the region has undergone repeated cycles of uplift, subsidence, and eruption, each leaving subtle marks on the landscape. The distribution of volcanic materials across the area reflects these cycles. Layers of ash and fragmented rock are spread across wide distances, sometimes forming soft, porous deposits that can be easily shaped by erosion. In other places, hardened lava flows create more resistant surfaces. These variations influence how water moves across the land, how vegetation takes root, and how human structures are built. Despite the calm appearance of the wider region, scientific measurements reveal ongoing activity beneath the surface. Instruments placed across the landscape detect small changes in elevation, shifts in ground position, and variations in gas emissions. These measurements provide a continuous record of the Earth's behavior, capturing details that are not visible to the eye. The data show that the region is not static, but part of an active geological system. Uncertainty remains in understanding how these processes will evolve. Observations indicate patterns of movement and change, but the exact timing and scale of future activity cannot be determined with precision. The complexity of the system arises from the interaction of many factors, including temperature, pressure, rock composition, and the presence of fluids. Each of these elements influences how energy is stored and released within the Earth. Within the wider Mediterranean context, the volcanic systems of southern Italy represent one expression of a broader pattern. Similar processes occur along other plate boundaries and volcanic regions around the world. What distinguishes this area is the close proximity of active geological features to densely populated communities. This relationship between natural processes and human presence creates a need for careful observation and understanding. The surface of the region continues to reflect a balance between stability and change. The land supports daily life, agriculture, and movement, while beneath it, slow transformations persist. The broader setting does not display immediate signs of instability, yet it remains connected to deeper forces that shape its long-term evolution. The calm of the coastline and the steady rhythm of the sea contrast with the gradual shifts occurring far below, forming a layered environment in which visible tranquility coexists with hidden activity. The Campanian coastal plain rests between the sea and the low volcanic hills west of Naples. It appears at first as an ordinary inhabited landscape, with roads, buildings, fields, ports, and narrow strips of shore arranged across ground that has been shaped by both nature and settlement. The plain is not a flat surface in the simple sense. It rises and falls in gentle steps, with shallow basins, coastal terraces, small ridges, and depressions that hold traces of older volcanic activity beneath later layers of soil, stone, and construction. This region belongs to the western side of the Bay of Naples, where the coastline bends around the city of Pozzuoli and the surrounding towns. The sea enters the land in sheltered inlets, and the land extends outward in low headlands. The boundary between water and ground has shifted many times through geological and historical change. In some places, the shore is firm and built upon. In others, it is shaped by soft volcanic deposits that erode more easily, leaving small cliffs, slopes, and uneven edges along the water. The visible surface contains many signs of long occupation. Streets follow older paths. Buildings stand close together in dense urban areas. Harbours, seawalls, and waterfront structures show how people have adapted the coastline for trade, fishing, travel, and daily life. The land is busy at the human scale, yet its deeper origin remains volcanic. Beneath foundations and pavements lie deposits of ash, pumice, tuff, and reworked sediment. Tuff is volcanic ash that has hardened into rock, and it is common across this part of Italy. The soils of the plain are products of weathering and time, rain, wind, roots, and human cultivation break down volcanic materials into darker, fertile ground. This fertility has helped support settlement for centuries. Gardens, orchards, and small agricultural plots occupy spaces where the land opens between towns. The same volcanic origin that creates productive soil also means the ground is layered with materials of different strength, density, and water content. Some layers hold water. Others allow it to pass through. These differences influence drainage, stability, and the way the surface responds to pressure from below. Around Pozzuoli, the coastal plain shows a close connection between geology and everyday surroundings. The town sits partly on ground that has risen and fallen over historical time. Ancient structures near the shore preserve evidence of changing sea level relative to land. This change is not only caused by the sea itself, it can also occur when the land moves upward or downward. In this region, measured ground movement is a known feature, and it has affected the relationship between buildings, roads, and the coastline. The surface setting includes areas of open ground, crater rims, lakes, and low hills that are part of the broader volcanic field. These features do not always look dramatic. Some are softened by vegetation or partly hidden by urban growth. A crater may appear as a rounded basin with houses along its slopes. A volcanic ridge may look like an ordinary hill. A depression may hold a lake or a flat space used by people. The quiet appearance of these forms can make the volcanic nature of the area less obvious. The coastal plain is also influenced by water from several sources. Rainfall drains through streets, fields, and natural channels. Groundwater moves through porous volcanic layers. Seawater borders the system and interacts with the shallow subsurface near the coast, where warm fluids rise from below. They can alter rocks and change the chemistry of water and soil. These processes occur unevenly, producing local differences across short distances. One area may remain cool and dry near the surface, while another may show warmth, steam, or mineral staining. Human settlement adds another layer to the region. Buildings, roads, tunnels, and underground services change how water moves and how the surface behaves. Construction can cover natural openings, cut through deposits, or place weight on ground with variable strength. These changes do not create the volcanic system, but they influence how its surface signs are seen and managed. In a densely inhabited plain, even small changes in ground level or minor earthquake shaking can have practical effects. The plain's position beside the bay gives it both shelter and exposure. The sea offers transport routes and economic value, while the low coastline can be sensitive to ground movement. When land rises, old marine surfaces may emerge. When land sinks, water can move farther inland or affect coastal structures. In this setting, the boundary between land and sea becomes a record of slow vertical motion. Scientists compare modern measurements with historical markers to understand how the surface has changed through time. The everyday view of the Campanian coastal plain is therefore layered. There is the visible layer of homes, streets, vegetation, and shore. Beneath it lies a layer of volcanic deposits, some young in geological terms and others much older. Beneath those are fractured rocks, warm fluids, and structures formed by earlier eruptions and collapses. Each layer affects the others, but the surface remains the place where these influences become important to people. Observations across the region indicate that the plain is not merely land beside a volcano. It is part of the volcanic system itself. Its shape, materials, water flow, and movement are connected to processes below. At the same time, the presence of towns and infrastructure gives the area a human meaning that differs from an uninhabited volcanic field. Scientific understanding must therefore include both the natural ground and the built environment resting upon it. The Campanian coastal plain holds a quiet tension between ordinary life and geological activity. The surface supports daily routines, traffic, markets, schools, ports, and homes. Its streets and buildings make the area appear settled and familiar, yet the ground beneath them is made from repeated volcanic events, altered by heat, water, and time. The plain is not a separate stage placed above the volcanic system. It is the outer inhabited skin of that system, where the first visible signs of deeper change are measured, recorded, and interpreted with care. The surface form of the caldera spreads across the Campanian landscape as a broad, shallow basin that does not immediately reveal its origin. A caldera is a large depression formed when a volcanic system empties part of its magma reservoir, and the ground above collapses into the space left behind. In this region, the caldera extends over many kilometers, and its boundaries are not marked by steep walls or sharp edges. Instead, they appear as gentle rises, subtle ridges, and variations in elevation that can be followed across the terrain with careful observation. The outer rim of the caldera is not continuous in a simple circular shape. It is broken and modified by later eruptions, erosion, and human development. In some areas, low hills trace parts of the original boundary, forming arcs that suggest the outline of the collapse. In other places, the rim is difficult to distinguish, blending into surrounding terrain or concealed beneath newer deposits. The result is a structure that must be interpreted through mapping, measurement, and comparison rather than seen as a single visible feature. Within the caldera, the ground is uneven and varied. Some areas rise slightly above the surrounding land, while others form depressions or basins. These differences reflect the complex history of collapse, infill, and later volcanic activity. After the initial formation of the caldera, subsequent eruptions produced cones, craters, and layers of ash that partially fill the depression. Over time, erosion and sedimentation further reshaped the surface, smoothing some features while preserving others. The caldera floor includes both natural and modified landscapes. Lakes occupy certain depressions, formed where water collects in low areas that intersect with the water table. One example is Lake Avernus, which lies within a volcanic crater that formed after the main collapse event. The lake's presence shows how water and volcanic structures interact at the surface, creating stable bodies of water in places where the ground has subsided or where impermeable layers prevent drainage. Other parts of the caldera floor support urban areas, roads, and infrastructure. Towns have grown across the basin, adapting to the available land and its contours. The built environment follows the shape of the terrain, with streets curving around slopes and buildings arranged along natural levels. In this way, the human landscape reflects the underlying volcanic form, even when the origin of that form is not immediately apparent. The surface materials across the caldera are diverse. Layers of ash, pumice, and tuff vary in thickness and composition. Some deposits are loose and porous, allowing water to pass through easily. Others are more compact, forming firmer ground. These differences influence how the land responds to rainfall, how vegetation grows, and how stable the surface is under weight. The distribution of these materials is not uniform, as each eruption contributed different types of deposits that spread unevenly across the area. The caldera's shape also influences drainage patterns. Rainwater collects in low areas and flows along paths determined by the terrain and the permeability of the ground. In some places, water infiltrates quickly into the subsurface, while in others it remains near the surface, forming temporary pools or feeding lakes. This interaction between water and volcanic material plays a role in shaping the landscape over time, gradually modifying slopes and filling depressions. Subtle changes in elevation across the caldera can be measured with modern instruments. These measurements reveal that the ground is not fixed. It rises and falls slowly in response to processes occurring beneath the surface. The movement is often uneven, with some areas lifting while others remain stable or sink slightly. This pattern reflects the distribution of pressure and fluid movement below, as well as the structure of the caldera itself. The visible features of the caldera provide clues to its formation and evolution. The arrangement of craters, cones, and ridges indicates multiple phases of activity. Some craters are aligned along fractures, suggesting pathways through which magma and gas reached the surface. Others are more isolated, marking localized eruptions. By studying these patterns, scientists reconstruct the sequence of events that shaped the caldera. Although some details remain uncertain due to erosion and overlapping deposits, the caldera's broad form creates a sense of openness across the landscape. There is no single central peak or dominant feature that defines it at a glance. Instead, the structure is distributed, with its identity emerging from the combination of many smaller elements. This distributed nature can make it less immediately recognizable as a volcanic feature compared to a steep-sided volcano, yet it represents a system capable of large-scale change, formed by events that release significant energy and reshape the ground over a wide area. Vegetation across the caldera softens its appearance. Grass, shrubs, and trees cover slopes and fill depressions, masking the raw surfaces of volcanic deposits. Over time, this vegetation contributes to soil formation, further blending the volcanic features into a more familiar landscape. Human activity adds to this effect, as cultivation and construction alter the surface and integrate it into daily life. Despite this blending, the caldera remains a distinct geological structure. Its boundaries, internal features, and ongoing movement are subjects of continuous study. Observations indicate that the system is still active at a low level, with processes beneath the surface influencing the shape and behavior of the ground. The caldera is not a static remnant of past activity, but part of a living system that evolves over time. Understanding the caldera's surface shape requires attention to both large-scale patterns and small details. The gentle slopes, scattered craters, and subtle ridges all contribute to a picture of gradual change and layered history. Each feature represents a stage in the development of the volcanic system, from initial collapse to later eruptions and ongoing modification. The surface, though quiet in appearance, carries the imprint of these processes, offering a record that can be read through careful observation. The caldera forms the structural framework for the regions that follow inward. Its surface defines the space within which deeper processes act, and its features provide the first visible signs of those processes. The ground above is shaped by what lies below, and the shape itself becomes a guide to understanding how the system functions. In this way, the caldera surface stands as both a result of past events and a boundary through which present activity is expressed. The historical eruption field within Campi Flegrei is spread across the caldera as a pattern of craters, cones, rings, and layered deposits. It does not form a single volcanic mountain. Instead, It records many separate eruptions that occur from different openings in the ground. Each opening marks a place where pressure, molten rock, gas, or hot water reaches the surface through fractures. Over time, these eruptions build a scattered landscape, with each feature preserving part of the system's history. The older record of activity is partly buried beneath later deposits, erosion, vegetation, and buildings. Even so, the broad pattern remains visible through geological mapping. Layers of volcanic material show that Campi Flegrei has produced eruptions of very different size and style. Some eruptions spread ash over wide areas, others build smaller cones or rings near the vent. The term vent means an opening through which volcanic material escapes. In this field, vents appear in many places, reflecting the fractured nature of the crust beneath the caldera. One of the most important ancient deposits in the region is the Campanian ignimbrite, formed by a very large eruption tens of thousands of years ago. An ignimbrite is a deposit made from hot mixtures of gas, ash, and rock fragments that flow rapidly across the ground during an explosive eruption. This event spreads material across a large part of southern Italy and contributes to the formation of the caldera structure. Its deposits are thick in some areas and thinner farther away, showing how volcanic flows and falling ash move across uneven terrain. A later major eruption forms the Neapolitan yellow tuff, another widespread deposit that becomes part of the region's geological and human history. This yellowish volcanic rock is visible in cliffs, quarries, and old building stones. Its colour comes from alteration after deposition, as hot fluids and time change the minerals within the ash. The deposit marks an eruption that reshapes the caldera and leaves material that later people cut, carve, and use in construction. After these large events, activity continues through smaller eruptions scattered across the caldera floor and margins. These eruptions produce crater lakes, tuff rings, cones of loose fragments, and layers of ash. A tuff ring forms when explosive activity builds a low circular ridge around a vent, often involving interaction between magma and water. Where rising magma meets groundwater or seawater, steam can form rapidly, increasing fragmentation and producing fine ash. Such eruptions may be brief in geological terms, yet they leave clear landforms. The field contains features such as Astroni, Solfatara, Averno, and Monte Nuovo. Each belongs to a different part of the eruption history. Astroni is a cratered structure with a broad interior that now supports vegetation and wildlife. Solfatara is known for steaming ground and altered rocks, though its form also reflects earlier eruptive activity. Averno holds a lake within a volcanic depression. Monte Nuovo is the youngest eruption site in the field, formed in the 16th century after a period of ground uplift and unrest. Monte Nuovo stands as a clear example of how a small eruption can change the surface quickly. Before its formation, the area near Pozzuoli experiences noticeable ground movement, changes along the coast, and reported disturbances. The eruption builds a cone over a short period, covering nearby land with ashen fragments. In comparison with the largest ancient eruptions, Monte Nuovo is small, but its importance lies in its historical documentation. It shows that the system can produce new vents within the inhabited caldera. The deposits around these vents vary according to eruption style. Some layers are coarse, made of blocks and lapilli, which are small volcanic stones thrown from a vent. Others are fine ash that can settle over broad areas. The thickness, grain size, and internal layering of deposits allow scientists to infer how eruptions unfold. A thick, coarse layer near a vent may suggest strong local explosions. thin, fine ash farther away may indicate material carried by wind before settling. Water plays an important role in many eruptions of the field. The caldera contains groundwater, lakes, and nearby seawater, all of which can interact with rising heat and magma. When water flashes into steam, it expands rapidly and can drive explosive activity. Such interactions are common in volcanic fields where vents open through water-rich ground. The resulting deposits can be fine-grained and widespread near the vent, with structures that show repeated bursts of activity. The historical eruption field also records periods of quiet between eruptions. During these intervals, soils form, vegetation returns, and people occupy the land. Later eruptions may cover older surfaces, preserving them as buried layers. These buried soils and archaeological remains help establish timing because they show pauses between volcanic events. The record is not perfectly complete, since erosion removes some deposits and human activity disturbs others, but enough remains to reconstruct a broad sequence. Scientific study of the field relies on mapping, mineral analysis, dating methods, and comparison of deposits. Dating methods help estimate when eruptions occurred, while chemical studies show relationships between different magmas. Observations indicate that activity has shifted across the caldera through time rather than remaining fixed at one central vent. This pattern supports the view of Campiflegrae as a distributed volcanic system, where future activity, if it occurs, would depend on the location of pressure pathways and fractures. The eruption field does not show constant activity at the surface. Most of the time, the craters and cones remain quiet landforms. They weather under rain, support plants, and become part of the inhabited landscape. Their calm appearance, however, does not erase their meaning. Each landform marks a place where the system once opened. Each deposit records material that moved from depth to surface and settled into the layered ground. Uncertainty remains in the interpretation of older deposits where layers overlap or have been altered. Some events are well constrained, while others are less clear. Observations indicate repeated explosive eruptions over long periods, but the exact sequence of every vent and deposit is still refined as new work is completed. This uncertainty is handled through careful comparison rather than assumption. The historical eruption field gives the caldera a memory written in rock. It shows that the surface is the product of many separate events rather than one simple formation. Across the landscape, crater rims, tuff rings, lake basins, cones, and ash layers preserve a record of changing pressure, water interaction, and magma movement. The field remains quiet in many places, but its forms describe how the system has behaved in the past, with each feature holding its place in the layered volcanic history of Campiflegrae. The present surface of Campiflegrae changes in ways that are slow, measurable, and uneven. The ground rises and falls over years to decades, creating a pattern known as bradyseism. Bradyseism means slow ground movement, especially uplift or sinking, often linked to pressure changes beneath a volcanic area. In this caldera, bradyseism is one of the clearest surface signs that the system remains active. It does not by itself mean that an eruption is beginning. It shows that the ground is responding to changes below. Around Pozzuoli, this movement has been observed for centuries. The coastline and ancient structures preserve signs that land level has shifted relative to the sea. Columns at the old Roman market, often called the Serapeum, show marks made by marine organisms at heights above the present sea level. These marks indicate that parts of the structure were once lower, allowing seawater to reach them, and later rose again. The columns provide a visible record of long-term vertical motion in the ground. Modern measurements make this movement clearer and more precise. Instruments now record changes in elevation across the caldera with high accuracy. Satellite radar, ground-based positioning systems, and leveling surveys show where uplift is strongest and how it changes through time. The greatest uplift in recent decades has been concentrated near Pozzuoli, close to the central part of the caldera. The movement decreases outward, forming a broad pattern rather than a sharp local bulge. The surface does not move as a single rigid block. Different areas rise at different rates, depending on the structure of the ground below. Some locations show steady uplift for a period, while others change more slowly. The pattern can pause, slow, or reverse. This uneven behavior reflects the complex interaction between rock, fluids, pressure, and fractures. The ground acts like a layered and fractured shell rather than a smooth elastic surface. During periods of stronger uplift, small cracks may appear in walls, roads, and older buildings. These cracks can result from ground strain, which means the stretching or bending of the surface as it adjusts to movement below. In urban areas, the effects are more noticeable because buildings and paved surfaces record small changes that bare ground may not show clearly. Damage patterns must be interpreted carefully, because ordinary settling, construction quality, and local soil conditions can also affect structures. The ground surface also changes near areas of heat and gas release, around fumarolic zones, where steam and volcanic gases escape. Soils may become warm, altered, or weakened. Minerals can form crusts at the surface as gases react with air, water, and rock. These altered areas may appear pale, yellowish, reddish, or grey, depending on the minerals present. Such surface changes are local, and they reflect chemical processes close to the ground. Uplift can influence drainage and coastal conditions. When land rises, the relative position of the shoreline changes. Old harbour edges, sea walls, and low coastal structures may shift in relation to the water. In Pozzuoli, changes in ground level have affected the use of port areas in the past. The land's vertical movement alters slopes and water flow in subtle ways, which can matter in places where human structures are close to sea level. Scientists measure the surface movement to understand its shape and timing. A repeated measurement at one point is useful, but a network of measurements across the caldera is more informative. The pattern of uplift can suggest where pressure is increasing beneath the surface. However, the source of that pressure may not be simple. It may involve movement of gas, heating and expansion of water, changes in a hydrothermal system, or input from magma at depth. Observations indicate that more than one process may contribute. The surface record contains episodes of stronger unrest. In the 20th century, two major uplift periods affect the area, with significant ground rise and increased earthquake activity. These episodes lead to concern because they show that the caldera can deform rapidly on human timescales. Later decades also show renewed uplift and repeated seismic swarms. The recent pattern is watched closely, not because it proves a specific outcome, but because persistent deformation is an important signal in an active caldera. The word alarming is often used in public discussion when ground movement increases. In scientific terms, the more careful description is unrest. Unrest means that a volcanic system is showing changes from its usual background state. At Campi Flegrei, unrest includes uplift, shallow earthquakes, gas changes, and heat flow in some zones. Each signal has meaning, but none stands alone as a definite prediction. The value lies in observing how signals evolve together. Surface deformation is especially important because it can continue without eruption. Many calderas experience unrest that does not lead to magma reaching the surface. The crust may bend and crack, pressure may rise and fall, and fluids may move without producing an eruption. This makes interpretation difficult. Observations indicate that Campi Flegrae is active and restless, but it remains uncertain whether any current or future unrest will culminate in eruptive activity. The texture of the land reflects this state of slow adjustment. Pavements, slopes, walls, and shorelines become quiet markers of change. A few centimeters of movement may seem small, yet over years it can become significant. When measured across a wide area, such movement reveals the scale of the pressure source below. The surface becomes a kind of instrument, responding to unseen changes in depth. Careful monitoring reduces uncertainty, but it does not remove it. Scientists compare present movement with past episodes, test models of pressure sources, and update interpretations as new data arrive. The ground itself remains the primary evidence. It rises, slows, shifts, and records stress in small fractures and changed levels. Its changes are not dramatic at every moment, but they are persistent enough to require attention. The present surface of Campi Flegrae is therefore not still. It is an inhabited ground that moves gradually, sometimes more quickly, under the influence of processes below, its roads, shores, ancient ruins, and buildings all rest on a caldera floor that continues to respond to pressure and heat. The changes are measured calmly, interpreted carefully, and placed within the wider pattern of volcanic unrest. The surface remains the outer visible expression of a deeper system that is active, complex and not fully predictable. Beneath the shifting surface of Campi Flegrae, small earthquakes occur in patterns that reflect the movement of stress within the upper crust. These earthquakes are usually shallow, often taking place within a few kilometers of the surface, and they tend to appear in clusters rather than as isolated events. A cluster of many small earthquakes in a short period is known as a swarm. In this caldera, swarms are a common feature of unrest, and they provide a detailed record of how the ground responds to changing pressure below. The earthquakes are generally low in magnitude, meaning they release relatively small amounts of energy compared with large tectonic earthquakes. Even so, they can be felt locally, especially when they occur close to the surface. Their importance lies less in their individual strength and more in their distribution, timing, and depth. By studying where and when these earthquakes occur, scientists gain insight into the structure of the crust and the forces acting within it. Seismic instruments placed across the region detect vibrations in the ground with high sensitivity. Each recorded signal contains information about the location, depth, and relative strength of an earthquake. By comparing signals from multiple stations, researchers calculate the position of each event. Over time, these positions form patterns that outline zones of activity beneath the caldera. These zones often align with known fractures or ring faults, which are curved breaks in the crust that mark the edges of the caldera structure. The relationship between earthquakes and ground movement is closely observed. Periods of increased uplift are often accompanied by more frequent seismic activity. This connection suggests that the same processes driving the ground upward are also causing stress to build and release along fractures. As pressure increases in the subsurface, rocks deform and eventually slip along these fractures, producing small earthquakes. When the pressure decreases or redistributes, the rate of earthquakes may decline. The depth of the earthquakes provides additional information. Many events occur at shallow levels, indicating that the stress is concentrated in the upper part of the crust. This region is influenced by changes in fluid pressure, temperature, and mechanical properties of the rock. Some earthquakes occur slightly deeper, suggesting that stress changes extend downward, though the majority remain within a limited depth range. The pattern indicates that the system's active zone is relatively close to the surface compared with deeper tectonic settings. Not all earthquakes in the region are identical. Some are sharp and sudden, reflecting brittle failure of rock where the material breaks abruptly under stress. Others are more gradual in their signal, indicating movement influenced by fluids or slower deformation. These differences help distinguish between purely mechanical fracturing and processes that involve the movement of gas or water through the crust. Observations indicate that both types occur within the caldera, contributing to a complex seismic picture. The timing of seismic swarms varies. Some swarms last only a few hours or days, while others extend over longer periods with fluctuating intensity. During more active phases, dozens or even hundreds of small earthquakes may be recorded in a short time. These episodes can draw attention because they are felt by residents and indicate a change from background conditions. However, similar swarms have occurred in the past without leading to eruptions, which adds to the challenge of interpretation. The spatial distribution of earthquakes is not uniform across the caldera. Activity often concentrates near certain zones, such as the area around Pozzuoli or beneath known fumarolic regions. This concentration reflects the presence of pathways through which pressure is transmitted. Fractures and faults act as channels where stress accumulates and is released. By mapping these zones, scientists identify the most active parts of the system and track how they evolve over time. The energy released by these earthquakes is small compared with the total energy involved in the volcanic system. Even during active periods, the seismic energy is only one expression of the underlying processes. Much of the system's energy is stored in heat, fluid pressure, and chemical interactions that do not produce strong seismic signals. The earthquakes therefore provide a partial view, highlighting areas of stress release while leaving other processes less visible. Seismic monitoring also reveals changes in wave speed through the ground. As conditions in the crust vary, the speed at which seismic waves travel can change slightly. These variations may indicate alterations in temperature, fluid content, or rock properties. For example, an increase in fluid pressure can reduce the effective stiffness of the rock, affecting how waves move through it. By analyzing these subtle changes, researchers refine their understanding of the subsurface environment. Uncertainty remains in linking seismic activity directly to specific causes. While patterns suggest connections with uplift and fluid movement, the exact mechanisms can differ from one swarm to another. Some swarms may be driven primarily by gas expansion, others by changes in hydrothermal circulation, and others by adjustments along faults. Observations indicate that multiple processes can operate at the same time, making the system complex to interpret. The presence of frequent small earthquakes indicates that the crust beneath Campi Flegrei is under persistent stress. This stress is not constant in intensity, but fluctuates as pressure builds and releases. The repeated occurrence of swarms shows that the system is active, with energy being redistributed through the crust. However, the absence of large earthquakes suggests that stress is often relieved in small increments, rather than through a single major event. In the inhabited areas above, these seismic patterns are experienced as occasional shaking, sometimes noticeable, sometimes barely felt. Buildings respond differently depending on their structure and the local ground conditions. While most events are minor, their frequency keeps attention focused on the underlying processes. The earthquakes serve as a direct connection between the hidden movements below and the lived experience at the surface. The seismic record of Campi Flegrae is therefore a continuous sequence of small adjustments within the crust. Each event marks a moment when stress overcomes resistance along a fracture. Together, they form a dynamic map of the system's internal state. The patterns they create are studied carefully, not as isolated signals but as part of an evolving network of observations. Through this network, the hidden processes beneath the caldera become partially visible, expressed in the quiet but persistent motion of the Earth. Across parts of the Campi Flegrae caldera, the ground releases gases and steam through openings that connect the surface to the shallow subsurface. These areas are known as fumarolic zones. A fumarole is a vent that emits steam and volcanic gases, often at elevated temperatures, without the presence of flowing lava. In this region, the most well-known fumarolic field lies at Solfatara, though smaller gas-emitting areas appear in other locations across the caldera. At the surface, these zones are marked by visible and chemical changes in the ground. Steam rises steadily from vents, sometimes in thin wisps and sometimes in thicker plumes, depending on temperature and pressure. The ground near these vents is often warm or hot to the touch. Surrounding rocks and soils show signs of alteration, with colours that range from pale white and yellow to red and grey. These colours result from chemical reactions between gases and minerals, which transform the original volcanic material into new compounds over time. The gases released from fumaroles are composed mainly of water vapour, along with carbon dioxide, sulfur dioxide, hydrogen sulfide, and smaller amounts of other compounds. Carbon dioxide is a colourless gas that can accumulate in low areas because it is heavier than air. Hydrogen sulfide has a characteristic odour and reacts easily with oxygen and minerals, forming sulfur deposits that appear as yellow crusts around vents. Sulfur dioxide is more reactive and contributes to the formation of acidic fluids when it dissolves in water. The temperature of fumarolic emissions varies from one vent to another. Some release steam at temperatures near the boiling point of water at the surface, while others may be cooler. Measurements at Solfatara indicate that temperatures can exceed 100 degrees Celsius in certain vents. These temperatures reflect the heat of the underlying system, though they are influenced by the mixing of hot fluids with cooler groundwater as they rise. The presence of gas emissions indicates that fluids are moving through the upper crust. These fluids originate from deeper levels, where heat from magma or hot rock drives the circulation of water and gases. As fluids rise, they follow fractures and permeable pathways in the rock. When they reach the surface, pressure decreases and dissolved gases escape, forming visible plumes. The pathways are not fixed. They can shift over time as fractures open, close, or change in permeability. The ground around fumarolic zones can be unstable. Continuous emission of gases and heat alters the structure of the rock, breaking it down into softer materials. Acidic fluids can dissolve minerals, weakening the ground and creating cavities or zones of low strength. In some areas, the surface may appear solid but conceals softer material beneath. This condition requires careful management in places where people may walk or work near active vents. Gas emissions are measured regularly to track changes in the volcanic system. Instruments collect samples and analyze the composition of gases, their temperature, and their rate of release. Changes in the proportion of gases, such as an increase in carbon dioxide relative to sulfur compounds, may indicate shifts in the source or pathway of fluids. Observations indicate that variations in gas output often accompany periods of increased ground movement and seismic activity, though the relationship is not always straightforward. Carbon dioxide emissions extend beyond visible fumaroles. The gas can diffuse through the soil over broader areas, escaping without forming visible plumes. This diffuse degassing can be measured by placing sensors on the ground or inserting probes into the soil. In some zones, the rate of carbon dioxide release is significantly higher than in surrounding areas. These zones may correspond to fractures or areas where gas accumulates below the surface before escaping. The interaction between gas emissions and water is important in shaping the surface environment. When gases dissolve in groundwater, they can create acidic solutions that alter rocks and soils. These solutions may emerge at the surface as warm or mineral-rich waters. Over time, the chemical alteration can change the appearance and properties of the ground, producing soft clays or mineral crusts. These changes affect how water moves through the soil and how stable the ground remains. Seasonal and weather conditions can influence how gas emissions appear at the surface. Rainfall may cool the ground, dilute surface expressions, or temporarily change the visibility of steam. Changes in atmospheric pressure can also affect the rate at which gases escape. Despite these variations, long-term measurements provide a clearer picture of trends in gas release, allowing scientists to distinguish between short-term fluctuations and sustained changes. Uncertainty remains in interpreting gas data. While increases in gas emission can indicate rising pressure or changes in the hydrothermal system, they do not necessarily signal that magma is moving toward the surface. Observations indicate that gas release can vary significantly without leading to eruptive activity. This complexity requires careful analysis and comparison with other signals, such as ground deformation and seismic patterns. The fumarolic zones serve as windows into the shallow part of the volcanic system. Through them, heat and gases that originate at depth reach the surface, providing direct evidence of ongoing processes. The steady emission of steam and gases shows that energy is being transferred upward, even during periods without eruption. These emissions are part of the normal activity of a caldera, though their intensity and composition can change over time. In the inhabited areas near these zones, the presence of gas requires attention to safety. High concentrations of carbon dioxide can pose risks in confined or low-lying spaces. Authorities monitor these conditions and manage access to areas where gas accumulation may occur. The balance between observation and safety reflects the need to study the system while protecting those who live and work nearby. The gas and steam zones of Campi Flegrei represent a visible and measurable aspect of the volcanic system. They connect the surface to the deeper circulation of fluids and heat, revealing processes that are otherwise hidden. Their behavior, though variable, contributes to the overall understanding of the caldera's state. Through continuous observation, these zones provide insight into how pressure, temperature, and chemistry evolve within the upper layers of the volcanic system. Below the gas and steam zones, the hydrothermal reservoir occupies a shallow inner part of the Campi Flegrei system. A hydrothermal reservoir is a body of hot water, steam, and dissolved gases held within fractured rock. It is not an open underground lake. It is a network of pores, cracks, and permeable layers where fluids move under pressure. In this region, the reservoir is heated from below and shaped by the rocks that surround it, creating a changing zone where water, heat, gas, and minerals interact. The water in this reservoir comes from several sources. Rainwater enters the ground from the surface and moves downward through porous volcanic deposits. Some seawater may also mix into the system near the coast. Deeper fluids rise from hotter regions below, carrying gases released by magma or hot rock. As these waters and gases meet, they form a complex mixture that changes with depth, temperature, and pressure. The exact proportions vary across the caldera, and they may change through time. Heat drives the movement of these fluids, Water warmed at depth becomes less dense and tends to rise, while cooler water from above moves downward to replace it. This circulation forms convection, which is the movement of fluid caused by differences in temperature and density. In a volcanic setting, convection can carry heat upward efficiently. It also transports dissolved minerals and gases, which can alter the rocks through which the fluids pass. Pressure within the hydrothermal reservoir is a central part of the system's behavior. When heat increases or gas is added, pressure can rise. When fractures open or fluids escape toward the surface, pressure can decrease. The rock around the reservoir responds to these changes by bending, cracking, or shifting slightly. This response can contribute to ground uplift and small earthquakes. The reservoir therefore acts as a shallow pressure chamber, though its boundaries are irregular and partly controlled by fractures. The fluids in the reservoir do not move freely everywhere. Some rock layers allow water and gas to pass through easily, while others are tighter and less permeable. Permeability means the ability of rock to let fluids move through it. Volcanic deposits can have high permeability when they are porous or fractured. Altered rocks can become less permeable when minerals fill pores and cracks. This creates zones where pressure may be trapped for a time before finding a pathway upward or sideways. Chemical reactions are continuous within the reservoir. Hot water dissolves minerals from the surrounding rocks and carries them through the system. As the fluid cools or reacts with gases, new minerals form. These minerals may seal fractures, reducing permeability. In other places, acidic fluids dissolve rock and enlarge pathways. The same system can therefore close some routes while opening others. This changing network affects how pressure is stored and released. Steam forms where water reaches conditions that allow boiling. Boiling can occur when hot fluid rises and pressure drops. As water turns to steam, it expands and separates from dissolved substances. This process can increase pressure locally and concentrate minerals in the remaining liquid. Steam and gas may then move upward toward fumaroles, while liquid water remains within deeper or cooler parts of the reservoir. The balance between liquid and vapor changes with temperature and pressure. Carbon dioxide plays an important role because it can move through rock and water differently from steam. It may dissolve in groundwater, form bubbles, or pass through fractures as gas. When carbon dioxide accumulates, it can increase pressure and affect the chemistry of fluids. It can also influence the acidity of water, helping dissolve minerals and alter rocks. Measurements of carbon dioxide at the surface provide clues about deeper degassing, but the path from source to surface is complex. The hydrothermal reservoir can amplify signals from deeper processes. A small increase in heat or gas input from below may produce a larger response in the shallow system if fluids expand, boil, or become trapped. This means that ground movement and gas emissions may change even without magma rising close to the surface. Observations indicate that hydrothermal processes are a major part of unrest at Campi Flegrei. It remains uncertain how much of any particular episode is driven by shallow fluid pressure and how much by deeper magma input. The reservoir also acts as a buffer. Fluids can absorb heat, redistribute pressure, and release gas gradually. This buffering may reduce sudden change in some conditions, while in others it may allow pressure to build behind sealed or low permeability zones. The behavior depends on the structure of the rocks, the amount of fluid present, and the rate of heat and gas supply. Because these conditions are hidden, scientists infer them from surface measurements, seismic data, gas chemistry, and models. Alteration within the reservoir changes the strength of the rocks. Hot acidic fluids can transform volcanic material into clay-rich zones that are weaker than the unaltered rock. Other mineral deposits can harden or seal parts of the system. These changes affect how the ground deforms. A weak zone may bend more easily, while a sealed zone may hold pressure until fractures reopen. The mechanical properties of the reservoir are therefore not fixed. They evolve as fluids continue to circulate. The depth of the hydrothermal system is shallow compared with the deeper magmatic source, but it is still beyond direct observation across most of the caldera. Wells, geophysical measurements, and surface emissions provide partial information. Each method has limits. Wells sample only specific locations. Seismic waves reveal broad structures but not every detail. Gas measurements show what escapes, not everything that remains below. The reservoir is understood through the combination of these lines of evidence. Within this hidden layer, water is not passive. It carries heat, stores pressure, alters rock, and transports gases. It connects the surface fumaroles with deeper sources of energy. It can make the system more responsive to small changes and more difficult to interpret. The hydrothermal reservoir is therefore a key inner region of Campi Flegrei, occupying the space where ordinary groundwater becomes part of a volcanic process. The calm surface above gives little direct sign of this complexity. Beneath it, fluids circulate through dark, fractured rock, warmed by heat from below and shaped by pressure from within. Some pathways lead upward to steam and gas, others remain sealed or slow. The reservoir changes gradually, responding to heat, gas, and the strength of the surrounding crust. Its behavior is measured indirectly, interpreted cautiously, and recognized as one of the main reasons the caldera remains active even in the absence of eruption. Below the hydrothermal reservoir, the rocks of Campi Flegrei carry stress through a fractured crust. This crust is not a uniform block. It is made of layers of volcanic deposits, older sedimentary rocks, hardened intrusions, altered zones, and faults formed during collapse and later movement. A fault is a break in rock where movement has occurred or can occur. In a caldera, faults often form curved or broken patterns around areas that have subsided, creating pathways where pressure and fluids may move. The stress within these rocks comes from several sources. The weight of overlying ground presses downward. Regional tectonic forces act across southern Italy. Heat changes the volume and strength of rocks. Fluids in cracks push outward against fracture walls. Deformation from deeper pressure bends the crust from below. These influences combine rather than acting separately, and the result is a crust that slowly adjusts through small movements, cracks, and changes in shape. Ring faults are important within the caldera structure. They form around zones of collapse, where blocks of ground have moved downward relative to surrounding areas. These faults may not be simple, smooth circles. They can be segmented, tilted, buried, or partly reactivated by later pressure changes. When the caldera floor rises or sinks, ring faults and related fractures can concentrate strain. This concentration makes them likely places for small earthquakes and fluid movement. The rocks within the caldera have different strengths. Loose ash and pumice near the surface may be weak and porous. Hardened tuff may be stronger, though it can fracture. Lava bodies and intrusive rocks may be denser and more resistant. Altered clay-rich zones may deform more easily. These differences create a layered mechanical structure. When pressure rises below, some layers bend, some crack, and some transmit stress to neighboring zones. Fractures provide both weakness and connection. A fracture can allow gas or water to move upward, but it can also close if pressure decreases or if minerals fill the opening. Some fractures remain open enough to carry fluids for long periods. Others open briefly during stress changes and then seal. This shifting pattern means the crust has a changing network of pathways. The same area may behave differently during separate episodes of unrest. Rock stress is not always visible at the surface. It may build quietly as pressure increases or as the ground bends. When stress exceeds the strength of a rock surface, the rock slips or breaks, producing a small earthquake. Many of the shallow earthquakes at Campi Flegrei are understood as brittle failure, which means the rock breaks suddenly rather than flowing smoothly. Brittle behavior is common in cooler upper crust, especially where fractures already exist. Temperature influences this behavior. Hotter rocks are generally weaker and may deform more gradually. Cooler rocks are more likely to break suddenly. In the caldera, the upper crust contains both heated zones and cooler areas. Depending on depth, fluid flow, and distance from heat sources. This creates uneven mechanical conditions. One part of the crust may crack under stress, while another bends or absorbs strain with less seismic activity. Fluid pressure changes the effective strength of faults and fractures. When water or gas pressure inside a crack increases, it pushes the fracture walls apart slightly. This reduces the force holding the surfaces together and can make slipping easier. In this way, fluids can trigger or encourage small earthquakes without requiring a large change in the total tectonic force. The movement of fluids through the crust is therefore closely linked to seismic activity. Stress transfer occurs when movement or pressure change in one area affects nearby areas. If one fracture slips, it can alter the stress on adjacent fractures. If the ground uplifts in one zone, surrounding rocks may be stretched or compressed. These changes can produce clusters of earthquakes that migrate or concentrate through time. The pattern does not always follow a simple path, because the crust is irregular and contains many old weaknesses. The caldera's past collapses have left a lasting imprint on its present stress field. Areas that moved during ancient events may remain mechanically different from surrounding rocks. Some faults may be easier to reactivate because they already contain broken material. Fault gouge, which is crushed rock along a fault surface, can be weaker than intact rock. This weak material may slip under lower stress, especially when fluids enter it. At the same time, some old pathways may be sealed. Minerals deposited from hydrothermal fluids can fill fractures and strengthen them temporarily. Sealed zones can trap pressure below or beside them. If pressure grows high enough, new fractures may form or old sealed fractures may reopen. This process may change the location of gas release, earthquake activity, or deformation. The crust is therefore both a barrier and a pathway. Scientists study rock stress and faults using earthquake locations, ground deformation patterns, gravity measurements, magnetic data, and geological mapping. Each method provides a different view. Earthquake patterns outline active fractures. Deformation shows how the crust bends. Gravity and magnetic measurements help reveal changes in rock density and structure. Surface mapping identifies faults and deposits that can be traced across the landscape. Together, these observations build a cautious picture of the hidden framework. Uncertainty remains because the fault network cannot be seen completely. Some faults are buried beneath younger deposits or urban areas. Some fractures are too small to map but still important for fluid flow. The exact strength of rocks at depth is difficult to measure directly. Observations indicate that the crust is highly fractured and mechanically complex, but the detailed arrangement of every pathway and weak zone remains uncertain. This uncertainty matters because volcanic unrest depends partly on how the crust responds to pressure. A strong sealed zone may allow pressure to build. A fractured permeable zone may allow fluids to escape more gradually. A fault close to failure may produce earthquakes when pressure changes only slightly. The same deeper process can therefore create different surface signals depending on the condition of the crust above it. Within this inner region, the caldera behaves as a stressed shell surrounding hotter and more pressurized zones. Its rocks preserve the memory of collapse, eruption, alteration, and repeated movement. They hold fractures that may open, close, slip, or seal. They transmit pressure upward and sideways. They shape where earthquakes occur and where gases can rise. The stress and fault system is not separate from the volcanic system. It is the rigid and broken framework through which the system expresses change. The fractured crust of Campi Flegrei remains under careful observation because it controls how hidden pressure becomes visible. It is the layer where slow bending turns into small earthquakes, where fluids find roots, and where old structures influence present behavior. Its movements are often slight, but their patterns carry meaning. In this region of broken rock, the caldera's unrest becomes a physical process of stress, weakness, resistance, and release. Deeper within the Campi Flegrei system, below the fractured upper crust and the shallow hydrothermal reservoir, the heat source is linked to magma held at depth. Magma is molten or partly molten rock that contains crystals, dissolved gases, and liquid melt. It is not a simple open pool. In many volcanic systems, magma exists as a mush-like region, where melt moves between crystals and hot solid rock. This region can store heat for long periods, release gases upward, and influence the shallow system without necessarily rising toward the surface. The magma source beneath Campi Flegrei belongs to a broader volcanic province created by tectonic processes in southern Italy. As plates interact, parts of the mantle and lower crust can melt under changing pressure, temperature, and fluid conditions. The resulting magma rises slowly because it is less dense than surrounding rock. Along the way, it may pause, cool, crystallize, mix with other magma, or release gases. These processes make the deep source complex and variable. At depth, pressure is much greater than near the surface. Under high pressure, gases such as water vapor, carbon dioxide, and sulfur compounds can remain dissolved in molten rock. As magma moves upward, or as pressure changes, some of these gases separate from the melt. This process is called degassing. Degassing can send fluids upward through fractures and permeable zones, supplying the hydrothermal reservoir above. The gases may reach the surface much later and in altered form, after mixing with groundwater and reacting with rock. The depth and shape of the magma source are inferred rather than directly seen. Scientists use seismic waves, ground deformation, gas chemistry, gravity measurements, and heat flow to estimate where hot material may be stored. These methods indicate that magma or magma-related heat exists below the caldera, but they do not produce a simple image of one chamber with sharp walls. The likely structure is distributed with hotter and cooler zones, partially molten regions, and pathways that change through time. The composition of erupted products from the past helps reveal the nature of the magma. Rocks and ash from Campi Flegrei contain minerals and glass that record temperature, pressure, and chemical evolution before eruption. Some deposits show evidence that magma resided at depth and changed through crystallization. Others suggest mixing between different magma batches. These records indicate that the system has stored magma in the crust during earlier periods of activity. Magma evolves as it cools. Crystals form and remove certain elements from the remaining melt. This changes the chemical composition of the liquid portion. Gas content also changes, especially if bubbles form and escape. The longer magma remains stored, the more it can differentiate, meaning it becomes chemically different from its original form. In explosive caldera systems, evolved magma can contain enough gas and viscosity to produce strong fragmentation if it reaches shallow levels under the right conditions. Viscosity is the resistance of a fluid to flow. Magma with higher viscosity moves more slowly and can trap gas more effectively. When gas remains trapped, pressure can build within the melt. If such magma rises and pressure drops, expanding gas can fragment it into ash and pumice. This process has occurred in past eruptions of Campi Flegrei, as shown by widespread deposits of fragmented volcanic material. However, the existence of magma at depth does not mean that eruption is occurring or about to occur. The deep heat source affects the system even during quiet periods. Heat moves upward through conduction and fluid circulation. Conduction is the transfer of heat through solid material. Fluid circulation carries heat more quickly when water and gas move through fractures. This heat sustains fumaroles, warms groundwater, and contributes to chemical alteration. The deep source, therefore, remains important even when no magma is rising into the shallow crust. Changes in the magma source may influence unrest. If new magma enters a deeper storage region, it can add heat, pressure, and gas. If gas separates from stored magma, it can move upward and pressurize shallow fluids. If the magma body cools or crystallizes, pressure may decline. These processes can create signals at the surface, such as uplift, seismicity, and changes in gas composition. Observations indicate that deep magmatic input may contribute to unrest episodes, but it remains uncertain how much is involved at any given time. A key challenge is distinguishing between magma movement and gas movement. Gas can travel faster and farther than melt. It can alter shallow pressures without the main body of magma rising. A surface signal may therefore reflect deep degassing rather than upward migration of molten rock. This distinction matters because the hazards and timescales can differ. Scientists compare multiple data streams to assess whether unrest is dominated by gas, hydrothermal pressure, rock stress, or possible magma intrusion. Magma intrusion means movement of magma into new rock space without necessarily reaching the surface. An intrusion can push surrounding rock aside, causing uplift and earthquakes. It can also heat groundwater and increase gas release. Some intrusions stop and cool underground, forming solid igneous bodies. Others may continue if pressure and pathways allow. At Campi Flegrei, possible intrusions are considered in models of unrest. But interpretations remain cautious because signals can overlap with hydrothermal processes. The source region is also shaped by the strength of the overlying crust. If the crust is fractured and permeable, gases may escape more readily. If it contains sealed zones, pressure may accumulate. The deep magma source and the overlying crust are therefore linked. Magma supplies heat and gas, while the crust controls how those influences move upward. The behavior of the whole system depends on both parts acting together. Past large eruptions show that Campi Flegrei has been capable of storing and releasing significant volumes of magma. These events belong to the long history of the system and do not define the immediate future by themselves. Present observations must be interpreted on their own terms. The current state involves ongoing unrest, shallow seismicity, uplift, and gas emissions. But it remains uncertain whether deeper magma is moving in a way that would lead to eruption. The magma source region is hidden from direct view, yet its influence is present throughout the system. It provides heat that drives circulation, gases that rise through fractures, and pressure that can affect the crust. Its behavior is slow in some periods and more active in others. The evidence comes through indirect measurements and the record of past deposits. From these clues, scientists build models that are useful but incomplete. In this deeper region, Campi Flegrei becomes less a landscape and more a thermal and chemical system. Hot rock, partial melt, crystals, and gases exist under pressure. They change gradually, interact with surrounding crust, and send energy upward. What is known is that magma-related heat and gas are present beneath the caldera. What remains uncertain is the exact arrangement of melt, the timing of any movement, and the future path of pressure through the system. The inner structure of Campi Flegrei is often described as a plumbing system, not in the sense of fixed pipes, but as a network of pathways through which heat, fluids, and pressure move between deeper and shallower regions. This system connects the magma source, the hydrothermal reservoir, the fractured crust, and the surface expressions such as fumaroles and ground deformation. It is not static. Its pathways open, close, shift, and evolve as conditions change within the caldera. At depth, gases released from magma rise into overlying rock layers. Some of these gases dissolve into groundwater, while others remain as separate phases that move through fractures. As they ascend, they encounter regions of different pressure and temperature. These changes affect how fluids behave. Gas may expand, water may boil, and chemical reactions may alter the surrounding rock. The plumbing system is therefore not only a set of routes but also a zone of transformation. Connections between regions are controlled by permeability and pressure gradients. Permeability determines how easily fluids can pass through rock, while pressure gradients drive movement from high-pressure zones to lower-pressure zones. In Campi Flegrei, both vary across short distances. A fracture that allows fluid flow at one time may become sealed by mineral deposition at another. A sealed zone may later reopen if pressure increases. This constant adjustment creates a system that is responsive but difficult to predict in detail. Vertical pathways are particularly important because they allow fluids and gases to travel upward from deeper levels toward the surface. These pathways may follow faults, fractures, or zones of weaker rock. Horizontal connections also exist, allowing fluids to spread laterally within permeable layers. The combination of vertical and horizontal movement creates a three-dimensional network rather than a simple upward flow. Fluids may circulate, pause, or change direction within this network before reaching the surface. The hydrothermal reservoir plays a central role within this plumbing system. It acts as an intermediary layer where fluids from depth mix with groundwater. Changes in the reservoir can influence the entire system. For example, if pressure rises within the reservoir, it can push fluids upward toward fumaroles and outward along fractures. If permeability decreases, pressure may build until new pathways form or old ones reopen. The reservoir is therefore both a conduit and a regulator. Chemical changes within the system affect its structure. As hot fluids move through rock, they can deposit minerals such as silica, sulfur compounds, or carbonates. These deposits may clog pores and fractures, reducing permeability. In other areas, acidic fluids dissolve minerals, enlarging pathways and increasing permeability. The system thus evolves through a balance between sealing and opening processes. This balance influences how pressure is stored and released. The movement of fluids and gases also affects the mechanical properties of the crust. When pressure builds in a confined zone, it can push against surrounding rock, contributing to uplift and stress. When fluids escape, pressure may drop, allowing the ground to settle or stabilize. These changes are often gradual, but they can produce measurable effects at the surface. The plumbing system translates deep processes into signals that can be detected by monitoring instruments. Observations indicate that the plumbing system can reorganize over time. During periods of unrest, new pathways may become active, while others become less important. This reorganization may be reflected in shifts in earthquake locations, changes in gas emission sites, or variations in deformation patterns. Such changes do not necessarily indicate a simple progression toward eruption. They show that the system is adjusting to internal conditions. The concept of a single central conduit is not sufficient for a caldera like Campi Flegrei. Instead, the system consists of multiple interconnected pathways. Some lead toward known fumarolic areas, while others may remain hidden beneath the surface. The distribution of vents in the historical eruption field supports this view, showing that eruptions have occurred in different locations across the caldera rather than from one persistent vent. Pressure within the plumbing system is not evenly distributed. It can concentrate in certain zones due to variations in permeability, temperature, or structural barriers. These localized pressure increases can lead to small earthquakes, increased gas emissions, or changes in ground movement when pressure is released. The system may return toward a lower state, though not necessarily to its previous condition. Each episode of unrest can alter the structure slightly. Monitoring efforts aim to track how this system behaves over time. By combining data from seismic activity, ground deformation, gas emissions, and temperature measurements, scientists build models of fluid movement and pressure changes. These models are tested against observations and adjusted as new data become available. The goal is not to produce a fixed map of the plumbing system, but to understand how it responds to different conditions. Uncertainty remains a defining feature of this inner region. The exact pathways of fluids cannot be mapped completely, and their behavior can change without direct visibility. Observations indicate patterns, but these patterns can shift. The system's complexity arises from the interaction of many variables, including heat, pressure, rock structure, and fluid composition. Each contributes to the overall behavior, and none acts alone. The plumbing system also acts as a mediator between deep magma and the surface environment. It determines how much heat and gas reach the upper layers and how quickly they move. If pathways are open, fluids may escape more easily, reducing pressure. If pathways are restricted, pressure may accumulate. This mediation influences the intensity and duration of surface signals such as uplift and gas release. The structure of the plumbing system reflects the history of the caldera. Past eruptions, collapses, and alterations have shaped the network of fractures and permeable zones. Each event leaves changes that influence future behavior. The system therefore carries a memory of previous activity in its structure, even when the surface appears unchanged. Within this network, the movement of fluids and gases is continuous. It may slow or accelerate, shift location, or change composition, but it does not cease entirely. The plumbing system sustains the connection between deep heat and surface expression. It is the pathway through which the caldera remains active over long periods, even in the absence of eruption. The inner structure of Campi Flegrei is thus a dynamic network rather than a fixed set of conduits. It links regions at different depths, transfers energy and material, and responds to changing conditions. Its behavior is observed through indirect signals and interpreted with care. Through this system, the hidden processes of the caldera find their way toward the surface, shaping the patterns of unrest that are measured and studied over time. Around Campi Flegrei, the monitoring network forms the outer sensing layer through which scientists follow changes in the caldera. The network is made of instruments placed across the ground, along the coast, near fumarolic areas, and in nearby observation centres. Each instrument records one part of the system's behaviour. No single measurement is enough to describe the whole caldera. The strength of monitoring comes from combining many signals and watching how they change together over time. Seismic stations record ground vibrations produced by earthquakes. These instruments are sensitive enough to detect small events that people may not feel. Each station measures motion in different directions, allowing scientists to calculate where an earthquake begins and how deep it occurs. When many stations record the same event, its location can be estimated more accurately. Over days, months, and years, the earthquake record becomes a map of active fractures and changing stress. Ground deformation is measured with several methods. Global navigation satellite systems, including instruments that receive signals from satellites, track the position of fixed points on the ground. These stations can detect small changes in height and horizontal movement. Leveling surveys compare elevation between points along measured routes. Satellite radar observes wide areas from space and detects changes in the distance between the satellite and the ground. Together, these methods show where uplift or subsidence is occurring and how its pattern changes. Gas monitoring stations measure the composition and amount of gases escaping from fumaroles and soils. Instruments sample carbon dioxide, sulfur compounds, water vapor, and other components. Some measurements are continuous, while others come from repeated field sampling. The chemistry of gases helps scientists understand whether emissions are changing because of shallow water circulation, deeper degassing, or shifting pathways through the rock. These interpretations are made cautiously because gases can be altered before they reach the surface. Temperature measurements provide another view of the system. Sensors record heat at fumaroles, in soils, and in selected ground areas. Thermal cameras and field instruments can detect changes in hot zones. A rise in temperature may reflect increased heat flow, changes in steam movement, or variations in shallow groundwater. A decrease may reflect cooling, rainfall effects, or changes in pathways. The meaning depends on context, and temperature data are compared with gas, seismic, and deformation records. Chemical monitoring extends to waters as well as gases. Springs, wells, and surface waters can contain dissolved minerals and gases that reflect interaction with the hydrothermal system. Scientists analyze these waters for changes in acidity, dissolved carbon dioxide, chloride, sulfate, and other substances. These changes may indicate mixing between groundwater, seawater, and deeper fluids. Water chemistry can respond slowly or locally, so it is treated as one piece of a wider pattern. Gravity measurements are used to detect small changes in the distribution of mass beneath the ground. If fluids move, if rock becomes more saturated, or if magma enters a region, the local gravity field can change slightly. These changes are very small, and careful corrections are needed for elevation, tides, and instrument drift. Gravity data are valuable because they can help distinguish between ground movement caused mainly by pressure and movement accompanied by changes in mass. Magnetic and electrical measurements provide information about rock properties and fluid distribution. Hot fluids and altered rocks can change the way the ground conducts electricity. Electrical resistivity surveys estimate how easily electric currents pass through the subsurface. Low resistivity may indicate clay alteration, saline water, or hot fluids. Magnetic measurements can reveal changes in minerals or temperature. These methods help define structures that cannot be reached directly. The monitoring network depends on continuity. Instruments must record through quiet periods as well as active periods. because background behavior is needed for comparison. A change has meaning only when there is a stable record showing what came before. Long-time series allow scientists to identify seasonal effects, instrument noise, and repeated patterns. They also show when the caldera departs from its usual range of behavior. Data from the network are checked and interpreted by scientific institutions responsible for volcano observation. In Italy, this work includes national monitoring and civil protection systems. The process involves automatic recording, human review, model testing, and communication with authorities. Data are not treated as isolated alarms. They are examined as part of an evolving assessment that considers uncertainty and the limits of each measurement. Alert levels are used to communicate the state of volcanic activity. These levels do not predict an eruption with certainty. They summarize the observed condition of the system and support decisions about planning and safety. A raised alert level means that unrest has increased or remains significant. It does not mean that an eruption is inevitable. The careful use of alert levels helps separate scientific observation from public fear. Models are built from monitoring data to test possible explanations. One model may represent pressure increasing in a shallow reservoir. Another may represent gas input from depth. Another may include the opening of fractures or changes in hydrothermal circulation. Models are simplified versions of a complex system. They are useful when they reproduce observations, but they remain incomplete. Scientists revise them when new measurements do not fit earlier assumptions. The network also records what does not happen. The absence of certain signals can be important. If deformation increases without matching changes in gas chemistry, one interpretation may become less likely. If earthquakes deepen or migrate, another interpretation may require attention. If gas output changes while ground movement remains steady, the system may be adjusting through fluid pathways rather than broad deformation. Each absence narrows the field of possible explanations. Though it does not remove uncertainty, monitoring near populated areas must be reliable and transparent. Instruments require maintenance, calibration, and protection from weather, corrosion, and human disturbance. Some stations sit in difficult environments where heat, acidic gases, and unstable ground can damage equipment. Keeping the network active is part of the scientific work. A failed instrument can create gaps. While a well-maintained station extends the record and improves understanding, the monitoring network does not control the caldera. It observes. Its purpose is to detect change early, describe it accurately, and provide evidence for decisions. The instruments do not make the system predictable in a simple way, but they reduce ignorance. They allow small movements, subtle gas shifts, and hidden earthquakes to be noticed before they become part of visible experience. At Campi Flegrei, this watching is continuous and measured. Signals rise and fall. Instruments record them without emotion. Scientists compare them with past behavior and with models of volcanic systems. The result is not certainty, but a disciplined awareness of change. Around the caldera, the network forms a quiet ring of attention, listening to the ground, measuring its motion, and following the movement of heat, gas, water, and stress through time. The hazard meaning of unrest at Campi Flegrei begins with careful separation between observation and prediction. Observations show that the caldera is active, with ground uplift, shallow earthquakes, gas emissions, heat flow, and changes in the hydrothermal system. These signals describe present behavior. They do not, by themselves, determine a single future outcome. In volcanic science, unrest means a departure from background conditions, not a confirmed path toward eruption. A caldera can remain restless for long periods without producing an eruption. Pressure may increase beneath the surface, rocks may fracture, fluids may move, and gases may escape while magma remains at depth. In such cases, unrest can be intense enough to affect people through earthquakes, ground deformation, gas exposure, or damage to buildings, even without eruptive activity. This distinction is important because hazards are not limited to eruption alone. The main observed hazards during unrest are shallow earthquakes and ground movement. Shallow earthquakes can be felt strongly near their source because seismic energy has little distance to weaken before reaching the surface. Even moderate events may disturb residents and affect vulnerable structures. Ground uplift can strain roads, pipes, walls, and coastal works. These effects may accumulate gradually, especially where older buildings or soft ground are present. Gas hazards also have practical meaning. Carbon dioxide can collect in low, enclosed, or poorly ventilated areas. Hydrogen sulfide and sulfur dioxide can irritate the airways and contribute to unsafe conditions near vents. Acidic fluids and altered ground can weaken surfaces in fumarolic zones. These hazards are local, but they require attention because they occur at the surface where people may live, work, or visit. An eruption, if one occurs, could take different forms depending on the location of a vent, the amount of magma involved, the presence of water, and the pressure conditions at the time. Past activity at Campi Flegrei includes explosive eruptions, tuff rings, ashfall, and pyroclastic deposits. Pyroclastic material is hot volcanic gas mixed with ash and rock fragments. The past record shows what the system has been capable of producing, but it does not specify what any future event must be. The most likely eruptive scenarios considered by scientists and authorities often focus on small to moderate explosive activity within the caldera, because this type of event is represented in the more recent geological record. Larger events are possible in the long history of the system, but they are less frequent. Hazard planning must consider a range of possibilities while giving weight to probability, evidence, and uncertainty. This approach avoids treating every unrest episode as if it must lead to the largest known outcome. Ashfall is one of the hazards that can extend beyond the immediate vent area. Fine ash can affect air quality, roads, water systems, agriculture, and machinery. Its distribution depends strongly on wind direction and eruption intensity. Even a relatively small explosive eruption can disrupt daily life if ash falls across populated zones. The severity varies with thickness, grain size, moisture, and the ability of communities to clean and manage the deposits. Near a vent, hazards may be more severe. Explosions can throw blocks and smaller fragments. Hot mixtures of gas and ash may move outward along the ground in some eruptive styles. Crater formation can alter local terrain. The exact area affected would depend on where the vent opens and how the eruption develops. Because Campi Flegrei is a distributed volcanic field, location is a central part of hazard assessment. Hydrothermal explosions are also considered within volcanic systems that contain hot water and steam. These explosions can occur when pressurized fluids flash into steam and fragment surrounding rock. They may happen without fresh magma reaching the surface. Their scale can vary, and they're generally local compared with magmatic eruptions. In a hydrothermal area, such events are difficult to anticipate precisely because they depend on shallow pressure conditions and sealed pathways. Scientific hazard assessment uses probability rather than certainty. A probability is an estimate of likelihood based on evidence, models, and past behavior. It does not promise an outcome. At Campi Flegrei, Assessments combine monitoring data with the geological record and physical understanding of caldera systems. When signals intensify, probabilities may be updated. When signals decline or stabilize, interpretations may also change. The process is continuous. Uncertainty exists at several levels. It remains uncertain how much current uplift is driven by shallow hydrothermal pressure, deeper gas input, or magma movement. It remains uncertain whether pressure will continue to rise, stabilize, or decrease. It remains uncertain where a vent would open if eruption occurred. These uncertainties are not gaps that can be filled by assumption. They are part of the system's nature and must be stated plainly. Hazard meaning also depends on exposure. Exposure means the presence of people, buildings, roads, services, and economic activity in areas where hazardous processes may occur. A volcanic event in an uninhabited region has a different human impact from the same event in a dense urban area. Campi Flegrei is significant because active ground lies beneath and beside towns, infrastructure, and cultural sites. The hazard is therefore both geological and social. Risk combines hazard with exposure and vulnerability. Vulnerability refers to how easily people or structures can be harmed. Older buildings, crowded districts, limited road capacity, and essential services near hazard zones can increase risk. Strong monitoring lowers uncertainty, but it does not remove exposure. Planning, communication, and building assessment become part of how society responds to the scientific meaning of unrest. The language used to describe unrest matters. Words that suggest certainty can mislead. Words that minimize change can also mislead. A balanced description states that Campi Flegrei is an active caldera in a period of unrest, that monitoring shows significant changes, and that the future course remains uncertain. This allows concern without exaggeration and preparedness without panic. The scientific consensus supports continuous monitoring, careful interpretation, and preparedness based on credible scenarios. It does not support simple claims that an eruption is imminent without clear evidence. It also does not support ignoring the system because many unrest episodes do not end in eruption. The correct position lies between these extremes, grounded in measured signals and updated understanding. The hazard meaning of Campi Flegrei is therefore layered. At the surface, unrest can affect daily life through shaking, deformation, gases, and local instability. In a possible eruption, hazards could include ash, explosions, and hot fragmental flows near the vent area. In planning, the main challenge is to act with seriousness while recognizing uncertainty. The caldera gives evidence of activity, but not a fixed timetable. Its signals require watchfulness, patience, and clear interpretation. The human risk zone around Campi Flegrei lies where volcanic processes meet dense settlement. Towns, roads, schools, hospitals, ports, railways, homes, and older buildings occupy ground that is part of the caldera. The risk does not come only from the presence of a volcanic system. It comes from the overlap between active ground and people who depend on that ground for daily life. In this region, science and public planning are joined by necessity. The area includes communities that have grown over many centuries. Streets often follow older routes, and buildings stand in districts shaped long before modern hazard planning existed. Some structures are recent and built with stronger materials. Others are older, altered, or weakened by age, moisture, poor maintenance, or past shaking. This mixture creates uneven vulnerability. The same earthquake may cause little damage in one building and more serious damage in another nearby building. Evacuation planning is central because the caldera is inhabited. Planning does not mean that an eruption is expected at a specific time. It means that authorities prepare for possible outcomes before conditions become urgent. Plans identify areas of concern, routes for movement, gathering points, transport needs, and the coordination required among local, regional, and national institutions. The purpose is to reduce confusion if scientific conditions require action. Movement through the risk zone is not simple. Roads pass through dense urban areas, narrow streets, coastal routes, tunnels, and connections toward Naples and surrounding regions. Traffic can become a hazard in itself if many people try to leave at once without coordination. Effective planning therefore depends on organized timing, clear instructions, and knowledge of where people live and how they may move. Vulnerable groups require particular attention, including older residents, people with disabilities, hospital patients, and those without private transport. Public communication is part of risk reduction. Residents need information that is accurate, calm, and understandable. Scientific terms must be explained without losing their meaning. Unrest, uplift, swarm, fumarole, and alert level each describe a specific condition. When these terms are used carefully, people can understand that the system is active without assuming that every change means immediate eruption. Clear communication helps prevent both panic and indifference. Buildings form a major part of the human risk zone. Shallow earthquakes can test walls, foundations, roofs, and older masonry. Ground deformation can slowly strain structures, especially where movement is uneven. Gas emissions can affect enclosed spaces and low areas. These hazards require different responses. Earthquake risk may call for structural assessment and strengthening. Ground movement may require inspection of roads, pipes, and buildings. Gas risk may require ventilation, restricted access, and monitoring in specific locations. Critical infrastructure has special importance. Hospitals, emergency centers, power lines, water systems, communication networks, fuel supplies, and transport links must continue functioning during unrest when possible. If these systems fail, the consequences extend beyond the immediate geological hazard. Planning therefore examines not only where people live, but also how services connect across the region. A damaged road, a closed port, or a disrupted communication line can change the effectiveness of any response. The presence of the sea shapes both risk and planning. Coastal areas may be affected by ground uplift or subsidence, which changes the relationship between land and water. Ports and waterfront infrastructure are important for movement and supply, but they also sit close to zones where ground level has changed in historical time. The coastline is therefore both a resource and a sensitive boundary. Its condition must be watched as part of the wider system. Daily life continues during unrest. People work, attend school, care for families, maintain businesses, and move through the region while scientists measure the ground. This continuity matters because long periods of unrest can create fatigue. If warnings remain elevated for months or years, attention may weaken. Preparedness must therefore be maintained without constant alarm. The challenge is to build habits of readiness that fit ordinary life. Education supports this readiness. Schools, community groups, and local institutions can help people understand what to do during earthquakes, where to find official information, and how evacuation plans are organized. The goal is not to make every resident a specialist. It is to make basic actions familiar before stress increases. Familiarity reduces hesitation and helps people follow coordinated instructions if needed. Authorities use scientific monitoring to guide decisions. but decisions also involve social conditions. A change in alert level may have economic effects, emotional effects, and practical consequences. Evacuation, if ordered, affects families, work, healthcare, housing, and public trust. These actions require evidence and careful judgment. Scientific uncertainty does not remove the need for decision-making. It makes transparent reasoning more important. The risk zone also contains cultural and historical heritage, ancient ruins, churches, archaeological sites, and older neighborhoods carry value beyond their physical structures. Ground movement, earthquakes, gas, and possible ashfall can affect these places. Protecting them is difficult because human safety must remain the priority. Yet their presence adds another layer to planning. Documentation, maintenance, and emergency preparation help reduce loss where possible. Economic life is intertwined with the caldera. Tourism, fishing, commerce, services, and local industries depend on stable access and public confidence. Unrest can affect livelihoods even without eruption, especially if earthquakes damage property or if public perception changes. Risk management, therefore, includes not only emergency response, but also support for communities living through uncertainty. The human burden of unrest can be gradual, quiet, and persistent. Trust is essential in this environment. People are more likely to follow guidance when information is consistent, evidence-based, and openly updated. Trust can weaken if risks are exaggerated or dismissed. A calm statement of what is known and unknown supports better decisions. When observations change, explanations must change with them. This is part of living with an active caldera, rather than treating risk as a single event. The human risk zone is therefore not a passive area waiting for geological change. It is an active social landscape that can prepare, adapt, learn, and reduce vulnerability. Monitoring instruments provide data, but communities, planners, engineers, health workers, teachers, and emergency services turn that data into practical readiness. The goal is not to control the volcanic system. The goal is to reduce harm where people and volcanic processes overlap. Campi Flegrei shows how risk is formed at the boundary between Earth and society. The ground carries heat, pressure, gas, and fractures. Above it, people build homes, keep routines, and make plans. The same surface belongs to both geology and human life. Understanding the risk zone means seeing these layers together, with care for the science and care for the people who live within its reach. The inner uncertainty of Campi Flegrei rests at the boundary between what instruments can show and what the volcanic system still conceals. Observations indicate that the caldera is active, restless, and changing. The ground rises in measured patterns. Earthquakes occur in shallow swarms. Gases escape from fumaroles and soils. Heat moves through water and fractured rock. These facts are known through repeated measurement. What remains uncertain is how these processes will combine through time. Scientific understanding begins with evidence. The evidence shows that Campi Flegrei is not dormant in a simple sense. It is a living caldera system with pressure, heat, fluids, and stress moving through its structure. This does not mean that an eruption is certain. It means that the system is capable of change and that its present unrest requires careful observation. The difference between capability and certainty is central to calm interpretation. A volcanic system can move through several outcomes. Pressure may continue to rise for a time and then stabilize. Fluids may find new pathways and reduce stress. Earthquakes may increase, decrease, or shift location. Gas chemistry may change as deeper and shallower fluids mix in different ways. These outcomes are not guesses about a fixed future. They are possible behaviors known from volcanic systems and from the history of caldera unrest. The main uncertainty lies in the connection between shallow signals and deeper causes. Ground uplift may be caused by pressure from hot fluids, gases released from magma, movement of molten rock, or a combination of these. Earthquakes may reflect cracking caused by uplift, fluid pressure, fault reactivation, or changing stress in altered rock. Gas changes may reflect deeper input, shallow boiling, or changes in pathways. Each signal carries meaning, but no signal speaks alone. Models help organize these observations. A model can represent pressure beneath the ground, the shape of a reservoir, the movement of fluids, or the bending of the crust. These models are useful when they match measurements, but they remain simplified versions of a more complex reality. The caldera contains irregular rocks, sealed fractures, open pathways, hot zones, cool zones, and changing fluids. No model captures every detail. The uncertainty is not a failure of science. It is a feature of studying a hidden system where direct access is limited. Instruments measure effects at the surface and within the shallow crust. They do not reveal every crack, every pressure pocket, or every movement of gas at depth. Scientists work by combining evidence, testing explanations, and revising interpretations when new data appear. This process gives the strongest available understanding while preserving caution. The past record helps but does not decide the future. Campiflegrae has produced large eruptions, smaller eruptions, long quiet periods, uplift, subsidence, and unrest without eruption. These records show the range of behavior possible within the system. They do not provide a calendar. They do not say when or where a future vent will open. They define context, not certainty. The present state is therefore described through probability and preparedness. Probability gives a measured way to express likelihood under uncertainty. Preparedness gives society a way to act without needing perfect prediction. Together, they allow decisions to be grounded in evidence rather than fear. A caldera does not need to be predictable in every detail for monitoring and planning to be meaningful. The inner uncertainty also includes the human side of interpretation. People seek clear answers when the ground moves. Science can provide careful statements about what is observed, what is changing, and what remains unknown. It cannot honestly turn an uncertain system into a simple promise. The most accurate language remains steady. Observations indicate unrest. The future course remains uncertain. Monitoring continues. Within the caldera, energy moves through layers that are hidden from sight. Heat rises from deep rock. Gases separate from magma and pass into fractures. Water circulates, boils, condenses, and reacts. Rocks bend, crack, seal, and reopen. Each process influences the others. A small change in one layer may produce a larger effect in another, or it may fade without major consequence. This interdependence is why the system must be watched as a whole. The word supervolcano is often used for large caldera systems capable of very large eruptions. In scientific use, the more precise focus is on the caldera, its past deposits, its current unrest, and its possible hazards. Campiflegrae has produced major eruptions in the past, but present monitoring does not show a simple certainty of an extreme event. The careful view is broader and quieter. It recognizes both the scale of the past and the limits of present knowledge. The inner uncertainty is also shaped by time. Geological processes may unfold over years, decades, centuries, or longer. Human concern often rises over days and weeks. Monitoring connects these scales by recording gradual changes with daily attention. A small movement today becomes meaningful when placed within years of data. A swarm of earthquakes becomes clearer when compared with earlier swarms. Time turns scattered signals into patterns. At the deepest level of interpretation, Campi Flegrei remains a system of known activity and unknown timing. It is neither silent nor fully readable. It gives evidence through movement, heat, gas, and shaking. It withholds certainty because its inner pathways are complex and changing. This balance defines the scientific position. The caldera is watched because it matters. It is described carefully because its future is not fixed in the data. The final view is calm and measured. Above the hidden system, the landscape holds towns, shorelines, roads, lakes, and fields. Beneath it, the rocks carry pressure and heat through fractured layers. Between these worlds, instruments record small changes and scientists interpret them with caution. What happened at Campi Flegrei is not a single moment, but a long process of volcanic formation, collapse, renewal, unrest, and observation. What is happening now is part of that continuing process, known in pieces, measured with care, and understood through patient attention to the ground. The caldera rests beneath the quiet surface of the Bay of Naples region, holding its long record in layers of ash, stone, heat, water, and fractured rock. Its present unrest remains measured rather than certain, watched through instruments that follow small earthquakes, ground movement, gases, and warmth rising from below. Each signal adds one part to the wider picture, and each part is interpreted with care. Campi Flegrei shows how Earth can appear calm while still changing slowly. The surface carries towns, roads, lakes, ports, and fields. Beneath that familiar ground, fluids move through hidden spaces, rocks bend under pressure, and gases rise along old fractures. These movements belong to a system shaped over many thousands of years, and they continue within limits that science observes without pretending to know every outcome. What is known remains important. The caldera is active. Its ground has risen and fallen before. Its shallow crust produces earthquake swarms. Its gases and steam show that heat is still present. What remains uncertain is the future path of that activity. The system may change, pause, or continue in restless balance. Careful monitoring gives the clearest view available. The story closes not with alarm, but with attention. A volcanic landscape is not only a place of past eruptions, it is a place where Earth keeps adjusting, slowly and quietly, through time. Around Campi Flegrei, people live above a deep and complicated system, and science follows its signs with patience. The ground remains watched, the evidence remains measured, and the unknown remains held with calm caution.